Okay, so in 9.1, we talked about correlation and if it was positive, negative, no correlation, nonlinear correlation, all of those different types of correlation. And then we ended up finding our correlation coefficient. So the stronger the correlation, the closer to positive 1 or negative 1 our R value was. And then negative was our negative correlation, positive was our positive correlation. So when we move into 9.2, we start talking about linear regression. So when we look at a scatter plot and we say, oh, that like generally goes in a positive line, a positive correlation, we could draw a line that would be like the line of best fit, for example. You talk a lot about that in Algebra 1 and Algebra 2 when you're doing regression. Now, if you're looking at this graph here, you have points on the line and then you have points above or below it. So those points above or below it are the actual points in your scatter plot. And then the points on the line are just like directly above or below it. So vertical lines from those points on the scatter plot to that line of best fit, for example. So, like these here would be your essentially observed Y values. And then these points on your line would be your predicted Y values for any given X value. The difference between those points, like your observed and your predicted Y values, remember the observed is the one that's not on the line, is called the residuals. Those can be positive, they can be negative, they can be zero. I'm gonna be perfectly honest with you. Residuals is not a huge deal in this section. You're not going to be asked to constantly find residuals. It's just a term that you need to make sure you know. So that D value here for any given line, that D value is just your observed Y value minus your predicted Y value. So a regression line or line of best fit is the line for which the sum of the squares of the residual is a minimum. So basically, it's going to go through those points with the smallest possible amount between those observed and those predicted Y values. So basically, it's going to be a line that is as close as it can possibly be to all those points in your scatter plot. When we talk about equations of regression lines, so that really doesn't change from Algebra 1 where you were writing the equation of a line, y equals mx plus b. M is still your slope, okay, so b is still your y-intercept. None of that has changed. The difference is that y hat. It's just y hat because y hat is your predicted values, like what it should be for your line of best fit. Whereas when we're actually writing equations of lines, it's not a scatter plot, so those y values are the y values. But nothing changes as far as what the line looks like. Okay, y equals mx plus b, slope is still m, y-intercept is still b. The difference does come into when we're finding the formulas for those two values. It's not just, the difference between your points for the slope like it is in Algebra 1. You've got to find all your sums. So the good news is you're finding the same sums that we were finding in 9.1. We're adding up all our x's, adding up all our y's, multiplying our x and our y values and adding those up, squaring our x values, adding those up, all that. So to find your slope, n times the sum of x times y minus the sum of x times the sum of y all over n times the sum of x squared minus the sum of x squared. B, your y-intercept. So this first part of that equation is the just basic way to write this, y bar minus m times x bar. Y bar and x bar, that's the same thing it would have been before. Remember that bar means it's a mean or an average. So it's the mean of all our x's for x bar, the mean of all our y's for y bar. If you feel like you're going to forget this one, the second half is perfectly fine to use. The sum of y divided by n minus m times the sum of x divided by n. So n is just the number of pairs of data still. That's not changing. So if you've got 10 points, n is 10. The regression line always passes through the point x bar, y bar. So whatever the mean of your x's and the mean of your y's are, if you do your regression line correctly, it's always going to go through that point. Okay, so let's look at an equation, or a problem where we find the equation, line of best fit. So in number 1, we're going back to that problem that we used about 3 times in section 1. Number of years out of school, money contributed to the school, all of that. So in section 1, we found the we did scatter plot and we found the correlation coefficient. So today we're just writing the line of best fit. So I'm going to just jot down all of those sums that we had from the first section. So remember, our years was x, our money was y. So the sum of our x values was 88. The sum of our y values was 56.7. The sum of x times y was 435.6. And the sum of x squared was 1,836. Now, I took those values straight out of section 1. It's the exact same data we had before. But remember, for the sum of x's, I'm just adding all my x values. The sum of y's, I'm adding all my y values. The sum of x times y, I'm multiplying my x and my y. So like 1 times 12.5, 10 times 8.7, 5 times 14.6, all the way. And then adding everything of those up. And then for the sum of x squared, I'm just squaring my x's. So like 1 squared, 10 squared, 5 squared, 15 squared, adding all of those up. So when we find our line of best fit, we have 7 pairs of data, so n is going to be 7. So our slope, we're going to do n times x times y, or the sum of x times y, which was 435.6, minus the sum of x times the sum of y. And then we're going to divide that by n times the sum of x squared minus the sum of x squared. So I'm going to just take care of all of that in my calculator. I'm going to go ahead and simplify the numerator and the denominator individually so that you can see what those individually equal. So I end up with negative 1940.4 in my numerator and 5108 in my denominator. And if I divide those, I end up with about negative 0.380. Generally, they do 3 decimals in the slope and y-intercept because you are very rarely going to get whole numbers, but as long as you have 2 decimals, that's fine. Okay, so I have a slope of negative 0.380. So when I find my y-intercept, that is going to be the sum of my y's divided by n. So 56.7 divided by 7 minus my slope, which was negative 0.380, times the sum of my x's, which was 88, divided by 7. So I'm going to multiply all my values, divide all my values, simplify that b value completely. And I'm going to end up with about 12.877. Now, if you round sooner, you might have a slightly different answer for that. It's best if you wait to round until the very end, so just use those whole decimal answers that your calculator gives you. But if you round early, that's not the end of the world. So the only thing you have left to do is to write your final equation. So y hat is going to equal negative 0.380x plus 12.877. Okay, so it's just a matter of plugging into formulas and then finding that slope and that y-intercept and plugging it back into your general equation. Okay, so what I want you to do is I want you to pause while you're watching this and work out number 2 on your own so that you can see how you're doing, if you're getting the hang of this and all that. And then once you're ready, hit play again and compare what you got to what I got. Okay, so I'm going to go ahead and I'm going to jot down what all my sums were. So the sum of x was 24.23. The sum of my y's, 673. The sum of x times y, 1,509.16. And the sum of x squared, 55.2033. So I have 11 data sets in number 2. So it's remember we're talking about Old Faithful's eruption times so the duration and the time between for x and y. So when I find that slope, I'm going to do my n value times the sum of x times y minus the sum of my x's times the sum of my y, all divided by n times the sum of x squared minus the sum of x squared. So when I work all that out, I get a slope of about 14.59. And now I'm going to find my y-intercept. So I'm doing the sum of my y's divided by my n value minus my slope times the sum of my x's divided by my n value, which is going to give me a y-intercept of about 29.036. Again, depending on how you round, where you round, those numbers could be slightly different, but they should be relatively close to that. So the only thing that you have to do after that is write your equation. So we got y hat equals 14.59x plus 29.036. Hopefully you did well on number 2. And our last problem, number 3 comes straight out of number 2. We're going to use that same regression equation that we had found in number 2. So y hat equals 14.59x plus 29.036. So when you're using your regression equation to predict values, what it's going to give you is your x value. So it's saying use the regression equation for Old Faithful to predict the time until the next eruption for each duration. So if we have Old Faithful erupt for 2 minutes, we want to know how long is it going to be in between that one and the next one if that eruption lasts for a full 2 minutes. So all we're going to do is we're going to plug that in for x. So y hat equals 14.59 times 2 plus 29.036. And that's going to give me about 58.216 minutes in between that 2-minute eruption and whatever the next one is. So for part B, I'd encourage you to pause this video and do the same thing for part B. Figure out how long until the next eruption if Old Faithful erupts for 3.32 minutes, but you're doing the same thing. Okay, so we're just going to plug in that 3.32 in for x. So 14.59 times 3.32. We're going to add the 29.036, which is going to give us about 72.806 minutes. That's all there is to section 2. Hopefully you feel pretty confident with that. I'll post the actual homework and in the announcements on our Google Docs and all of that. But it's on page 490 and you're going to do numbers 2 through 30 even. Again, make sure you are showing your work. If you're not showing your work, it's going to be really hard for me to give you the credit for it. So don't just write the answer down, because if you just write the answer down, I know you either got it off of the internet or you texted somebody in class to give you the answer. So show me your work, okay?